Hello everyone and welcome back to today's lecture on energy efficient buildings. My name is Mohammad Etisham and our focus today will continue on lecture 33 of module 10, energy auditing and performance management. As we know, energy auditing and performance management are essential tools for organizations seeking to optimize their energy consumption and reduce cost. By conducting comprehensive assessment of energy usage, identifying inefficiencies, and implementing targeted conservation measures, business can significantly improve their energy efficiency, minimize environmental impact, and enhance their overall sustainability performance. Previously, we have already discussed energy auditing and management. Energy management aims to optimize energy use to minimize cost and environmental impacts, integrating it into company strategy for competitive advantage. An energy audit systematically evaluates energy flows to identify saving opportunities, balancing energy inputs with usage, and pinpointing inefficiencies. There were three types of energy audits discussed: preliminary, targeted, and detailed, each varying in scope and depth. The audit process involves pre-audit planning, data collection during the audit, and post-audit implementation of recommendations, identifying energy conservation opportunities, also known as ENCON, focuses on efficiency improvements and fuel substitutions. Assessed for technical and economic feasibility, the audit report includes an executive summary, detailed analysis, and prioritized recommendations for energy conservation measures, guiding strategic decision making and implementation. In this lecture, we'll be discussing the energy cost, energy audit tools and instruments, example of case study findings of a building audit, regulatory aspects, energy audit role in sustainability, and the conclusion. Understanding energy cost. Today, we'll explore how energy cost, often perceived as a fixed overhead, presents significant opportunities for savings. By gaining a comprehensive understanding of these costs, we can enhance awareness and accurately calculate potential savings. In many industries, adequate meters to measure all energy usage might not be available. In such cases, invoices for fuels and electricity become invaluable. These documents, along with the annual company balance sheet, provide insights into fuel and power cost related to production. Invoices are more than just bills. They offer a record of energy purchases, which serves as a baseline for future reference. They can highlight potential savings when compared to production or heating and cooling requirements. Over time, they quantify the energy and cost savings achieved through conservation measures. From the perspective of fuel cost, a diverse array of fuels is available for thermal energy supply, including fuel oil, LSHS, LDO, LPG, coal, lignite, and wood. Understanding fuel cost involves considering several factors. When procuring fuels, consider the price at the source, transportation charges, and the type of transport. Quality is crucial as contamination and moisture can affect performance. Finally, assess the energy content or calorific value, which determines the fuel efficiency and cost effectiveness. From power cost perspective, electricity prices in India vary widely, not just from state to state, but even city to city and among different consumer categories. Despite performing the same work, the final cost of electricity depends on various or several factors. From utility manager perspective, key factors include maximum demand charges, which relate to how fast electricity is used, and energy charges based on consumption. Time of day charges reflect peak and non-peak usage periods. Power factor charges accounts for the efficiency of power use. Other considerations include tariffs, incentives, and penalties, which can fluctuate based on location and consumer type. By understanding all these components, industries can strategically manage their energy consumption, leading to improved efficiency and reduced expenses. In conclusion, understanding energy cost is not just about paying bills, it's about strategic management and identifying opportunities for savings. By analyzing invoices and understanding the factors affecting fuel and power cost, industries can make informed decisions to enhance energy efficiency and reduce the costs. Which leads us to the next topic, benchmarking. Benchmarking in energy management. How benchmarking serves as a powerful tool for understanding energy consumption patterns and enhancing energy efficiency across various industries. Its purpose and importance. Benchmarking is not just about comparison, it's about setting a standard for excellence. It helps industries identify where they stand in terms of energy performance and where improvements can be made. From the perspective of energy analyst, by using benchmarking, we can monitor energy consumption and set realistic targets for improvement. The key metric here is energy intensity, which measures energy use per unit of output. This allows for effective comparisons regardless of plant size or output. There are many approaches to benchmarking, each tailored to different need and context. From the point of view of industry expert, first we have sector evaluation, which assess the performance of an entire industry like iron and steel or cement. This approach helps us to understand how well a sector is performing compared to the best available technologies and similar sectors globally. Next, there is individual plant comparison. Here we calculate a benchmark indicator for each facility within a sector. This allows us to see how a plant measure up against the state of the art and other plants in the same sector. Lastly, we have internal benchmarking for large companies. From the perspective of a corporate strategist, companies set energy efficiency goals based on their historical best performance. This approach helps them reduce energy use over time without disclosing proprietary information. Benchmark parameters are crucial for meaningful comparisons. For production related metrics, we look at specific energy consumption figures like kilowatt hour per ton of cement produced or kilocalorie per kilowatt hour of power generated. These metrics may vary by industry or help pinpoint areas for improvement. From the point of utility specialist, for equipment and utility related metrics, we focus on things like thermal efficiency of boilers or kilowatt hour per ton of refrigeration in air conditioning plants. These metrics provide insights into the efficiency of specific equipment, guiding targeted improvements. In conclusion, benchmarking is a vital tool in energy management. It not only helps industries understand their current energy performance but also sets the stage for continuous improvement. By adopting the right benchmarking approach and metrics, industries can enhance their energy efficiency and achieve significant cost savings. Moving ahead, let's talk about energy performance. Energy performance, a critical aspect of energy management in industrial settings. Plant energy performance or PEP is used to measure improvements in energy use over the time. Plant energy performance or PEP is a metric that evaluates whether a plant is using more or less energy to produce its product compared to previous years. Is a direct measure of how effective an energy management program is. PEP involves comparing a plant energy use from a reference year to subsequent years. This comparison helps us understand the improvements or deteriorations in energy efficiency. However, since production output can vary year to year, we need a method to account for these changes. So, the measurement of energy use improvement over time. To accurately measure energy use improvements, we must consider the production factor and reference year, equivalent energy use. The production factor is the ratio of current year's production to that of the reference year. It helps us determine the energy that would have been required to produce the current year's output, assuming the plant operated as it did in the reference year. We then calculate the reference year equivalent energy use by multiplying the reference year energy use by the production factor. This value represents the energy that would have been used under the same conditions as the reference year. Use of production factors and reference year equivalent energy use refers to once we have the reference year equivalent, we can determine plant's energy performance. To calculate the energy performance, we subtract the current year's actual energy use from the reference year equivalent. The result is then divided by the reference year equivalent and multiplied by 100 to express it as a percentage. This percentage reflects the energy saved at the current rate of use compared to the reference year. This method provides a clear picture of energy savings and efficiency improvements, allowing plants to track progress and make informed decisions about energy management. In conclusion, plant energy performance is a vital role for assessing and improving energy efficiency in industrial operations. By using the production factor and reference year equivalent energy use, plants can accurately measure their energy performance over time, leading to more effective energy management strategies. The next slide will be discussing matching energy usage to the requirement. We further explore strategies for aligning equipment capacity with user needs to enhance energy efficiency and reduce wastage. To get a better understanding, we need to understand the mismatch. In many industrial settings, there's often a mismatch between equipment capacity and user requirements. This mismatch can lead to inefficiencies such as part load operations and energy wastage. Energy managers or designers often build in safety margins when specifying equipment, which can result in oversized equipment. While this ensures reliability, it also presents an opportunity for energy managers to optimize and match equipment capacity more closely with actual needs. Strategies for managing energy usage. Second, let's look at some strategies to better match energy usage with requirements. One effective strategy is to eliminate throttling in pumps. This can be achieved by trimming the impeller, resizing the pump, or installing variable speed drives. These adjustments allow the pump to operate more efficiently at the required capacity. For fans, we can eliminate damper operations by similar methods: impeller trimming, installing variable speed drives, modifying pulley diameters for belt drives, or resizing the fan for better efficiency. In processes which requires chill water, moderating the water temperature to align with the process needs can also save energy. Additionally, recovering energy lost in control valve pressure drops by adopting back pressure turbines can further enhance efficiency. From lighting perspective, switching from area lighting to task lighting is another strategy. Task lighting focuses light where it's needed, reducing energy consumption compared to less effective area lighting, which can be attained through smart automated system, which we have already discussed in our previous modules. In conclusion, matching energy usage to requirements is a key strategy for reducing energy waste and improving efficiency. By aligning equipment capacity with actual user needs, industry can achieve significant energy savings. Moving ahead, maximizing system efficiencies. Let's continue with an understanding of maximizing system efficiencies. We'll discuss how operational improvements and technology adoption can significantly enhance energy efficiency in industrial processes. For operational improvements, once energy usage and sources are properly matched, the next step is to operate equipment efficiently. This involves implementing best practices in operation and maintenance. For the purpose, maintenance manager, one of the key actions is to eliminate steam leakages by improving steam traps. This not only conserves energy but also reduces operational cost. Maximizing condensate recovery is another effective strategy. By capturing and reusing condensate, we can significantly reduce the energy required to heat new water. This decision can be made by process engineers. Combustion specialist refers adopting advanced combustion controls help maximize combustion efficiency. This ensures that fuel is burned more completely, reducing waste and emission. Examples of improving system efficiency through maintenance and technology. Let's look at some specific examples of how maintenance and technology can improve system efficiencies. Replacing outdated pumps, fans, air compressors, refrigeration compressors, boilers, and furnaces with more efficient models can lead to substantial energy savings. These upgrades often have significant efficiency margins. Ensuring that motors operate at their rated electrical parameters is crucial. This involves regular maintenance checks to prevent energy losses due to inefficiency. This decision can be taken by electrical engineers. Incorporating technologies like variable speed drives can also optimize the operation of motors and pumps. allowing them to adjust their speed to match the actual demand. This reduces energy consumption during periods of lower demand. These decisions can be done by technology advisors. In conclusion, maximizing system efficiency is about more than just using less energy, it's also about using energy smarter. By implementing operational improvements and adapting the latest technologies, industries can achieve significant energy savings and enhance their overall efficiency. For optimizing the input energy requirements, we'll explore how industries can minimize energy inputs through strategic heat recovery and adoption of renewable energy resources, previously discussed in all the modules. Optimizing energy input is about using less energy to achieve the same and better outcomes. This involves fine-tuning energy use practices, implementing measures to reduce the overall energy needed for the operations. One of the primary methods for minimizing energy input is maximizing heat recovery. By capturing and reusing waste heat from industrial processes, we can significantly reduce the amount of purchased energy needed. This not only lower cost but also enhances overall energy efficiency. Moving ahead with strategies for maximizing heat recovery. Let's discuss few strategies for maximizing heat recovery. Implementing waste heat recovery systems is crucial. These systems capture excess heat from industrial process and convert it into useful energy such as steam or electricity. This recovered energy can then be used for power generation or additional manufacturing application, reducing the need for external energy sources. Advancement in heat exchanger designs and materials have made it easier to integrate these systems into existing operations. By improving the efficiency of heat exchangers, industries can extract maximum energy from waste heat sources, enhancing process efficiency. Further, we also have the use of renewable energy. In addition to heat recovery, integrating renewable energy resources is a powerful strategy for optimizing energy inputs. Renewable Energy Advisor can help you in adopting renewable energy sources like solar, wind, or biomass, which significantly reduce dependence on traditional energy sources. For instance, solar panels can provide electricity, while biomass can be used for heating, both of which reduce the need for fossil fuels. Sustainability consultant advises cogeneration plants are another effective solution. These plants simultaneously produce heat and power, balancing energy requirements and reducing overall energy purchases. By using renewable resources in cogeneration, industries can further enhance their sustainability efforts. In conclusion, optimizing input energy requirements through heat recovery and renewable energy adoption is a strategic move for industries aiming to improve efficiency and sustainability. By implementing these strategies, companies can achieve significant energy savings and contribute to a greener future. Moving ahead, instruments and metering for energy audit. In energy audits, the use of specialized instrument is essential for accurately measuring and analyzing energy consumption. These tools and instruments are designed to be portable, durable, easy to operate, and cost effective, making them ideal for on-site measurements. Let's have a discussion on few of the common instruments used in energy audits. Starting with electrical measuring instruments. These are crucial for assessing key electrical parameters such as kilowatt amperes, kilowatt, power factor hertz, kilowatt ampere reactive, amperes, and volts. Some advanced models can also measure harmonics. These instruments are used online, allowing measurements on running motors without stopping them. Handheld meters provide instant readings, while advanced models offer cumulative data with printouts at specified intervals. Followed by safety measures. To ensure safety, avoid attaching clamp to circuits operating above the maximum rated voltage or on bare conductors. Use rubber gloves, boots, and helmets to prevent electrical shocks, and avoid using instruments with wet hands. Fried gas analyzer. Fried gas analyzer measures the concentration of gases such as carbon dioxide and oxygen in the flue gases. It uses a hand blow pump to draw the gas sample into the solution, where a chemical reaction changes the liquid volume, indicating the gas percentage. This method, known as the Audit method, uses specific reagents to absorb gases. The Fry's unique feature is that absorbing fluid also serves as the indicating fluid. Fuel efficiency monitor. This instrument measures oxygen levels and the temperature of flue gas. It calculates combustion efficiency by using calorific values of common fuels fed into the microprocessor. Combustion gas analyzer have built-in chemical cells to measure various gases like CO2, CO, NO2 or SO3. They are flexible and can be configured to measure different components based on user requirements. Next is manometer with pitted tube. A digital flexible membrane manometer measures pressures in air ducts carrying exhaust gases. It uses a pitted tube to ensure accurate pressure measurements. Next in the list are thermometers, which comprises of number 1, contact thermometers. It measures the temperature of flue gas, hot air and hot water by inserting a probe into the stream. Non-contact infrared thermometer calculates temperature by measuring thermal radiation emitted by objects ideal for hazardous or hard to reach areas. Followed by ultrasonic flow meter. This non-contact flow measurement tool uses ultrasonic signals to determine the flow rates. There are main two types, transit type and Doppler, suitable for clean and dirty liquids respectively. Next is speed measurements, which comprises of tachometer, a contact instrument for measuring speed where direct access is possible. Followed by stroboscope, a non-contact instrument that uses high intensity light flashes to measure rotational speeds. The next one is psychrometer. A psychrometer consists of two thermometers to measure dry and wet bulb temperatures, allowing for humidity computation by comparing temperature differences. Next in the list are lux meters. Lux meters are essential for measuring light intensity in the visible spectrum. They use a light sensitive cell to evaluate incident light against the human daylight sensitivity curve, providing a measurement in lux. While effective, they require current and different correction factors for each light spectrum. Advanced lux meters are optimized with optical fibers and lenses to match the eye's light sensitivity curve, simplifying the correction process. Followed by the list are smart energy meters. They are typically used to monitor electricity usage, but they can also track fuels or waters. These devices provide real-time data on electricity consumption, helping users optimize their energy use and reduce the cost. They utilizes wireless communication for easy monitoring and control through mobile devices or the internet. Next are thermography. Infrared thermal monitoring and imaging or thermography measures thermal energy radiation from surfaces. This non-contact methods help assess equipment health and supports predictive maintenance by identifying hot or cold spots. The thermal camera converts infrared radiation into electronic video signals, which are analyzed to interpret temperature variations. All these instruments are integral to conducting thorough energy audits, providing the precise data needed to identify inefficiencies and recommend improvements for energy savings. By employing this tool, auditors can effectively enhance energy efficiency and reduce operational cost. Be it example of industries, be it example of commercial or residential. These tools are equally deployable at all the audits and at all the phases. Let's discuss the case study example of a residential building energy audit. A residential building energy audit is a detailed evaluation of a home energy consumption with the aim of identifying inefficiencies and recommending improvements to enhance the energy efficiency. This process involves several steps and can provide significant benefits in terms of cost savings, environmental impact, and improved comfort. Below is the Below we'll be discussing an explanation of how this audit incorporating example and insights. What are the steps involved in a residential building energy audit? As discussed previous in lectures, preliminary preparation. The initial stage involves gathering data on the building energy consumption. This includes reviewing past energy bills to establish a baseline for energy use. It is crucial to identify key personnel who can provide insights into the building operations and energy use pattern. Site inspection. A thorough inspection of the building is conducted to assess the structural components that affect energy efficiency, such as insulation, windows, doors. These steps may involve using diagnostic tools like infrared cameras to detect heat loss and blower door tests to identify air leaks. Data collection and analysis. During the audit, data is collected on the building energy systems, including HVAC, lighting, and appliances. The information is analyzed to identify patterns and areas of inefficiency. Techniques such as regression analysis and benchmarking against similar buildings can be used to understand energy consumption trends. Followed by technical assessment. The audit involves a technical assessment of various systems within the building. For example, the condition of the HVAC system, lighting efficiency, and the performance of appliances are evaluated to identify opportunities for improvement. This may involve checking the insulation of pipes, assessing the efficiency of boilers, evaluating the effectiveness of lighting control, understanding the daylight factor, understanding the sound and heat insulation with respect to the material picked for the structure, which leads to reporting and recommendation. The findings of the audit are compiled into a comprehensive report that outlines the current energy performance and provides recommendation for improvements. This report includes potential energy saving measures, estimated cost savings, and the financial feasibility of implementing these measures. Leading to implementation and the follow-up. Based on the audit report, homeowners can implement the recommended measures to improve energy efficiency. This may include upgrading insulation, installing energy efficient lighting, or integrating renewable energy sources like solar panels. Follow-up assessment can be conducted to monitor the effectiveness of these improvements, which leads us to the examples and insights of any energy audit case studies. We get outputs like lighting improvements. Replacing incandescent bulbs with LED lighting can significantly reduce energy consumption. Installing motion sensors and daylight link controls can further enhance lighting efficiency by ensuring lights are only on when it's needed. HVAC system optimization. Ensuring that HVAC systems are properly maintained and optimized for efficiency can lead to substantial energy savings. This might involve installing programmable thermostats, sealing ductwork, and upgrading to more efficient units. For insulation and air sealing, improving the building envelope by adding insulation and sealing air leaks can reduce heating and cooling demands. This not only lowers energy bills but also enhances indoor comfort. Renewable energy integration. Incorporating renewable energy resources such as solar panels can offset energy consumption from non-renewable sources. This is particularly effective in regions with high solar potential and can lead to long-term cost savings. All this leads to what are the benefits of energy audits. To start with, first is cost savings. By identifying and addressing inefficiencies, energy audits can lead to significant reductions in utility bills. Next, environmental impact. Energy audits help reduce carbon emission by promoting energy efficient practices and the use of renewable energy. Followed by improved comfort. Enhancement in insulation and HVAC systems can improve indoor air quality and overall comfort. Sustainability. Energy audits contribute to sustainable living by encouraging efficient use of resources and reducing an environmental impact. In conclusion, our residential building energy audit is a valuable tool for homeowners looking to improve energy efficiency, reduce cost, and minimize environmental impact. By following a structured approach and implementing recommended measures, significant improvements in energy performance can be achieved. To sum it up, energy efficiency measures with the help of auditing and management aims to decrease energy consumption while maintaining or enhancing comfort levels. These measures can be categorized into several key areas like reducing the heating demand by implementing insulation and utilizing energy efficient heating systems to lower the energy demand, like reducing cooling demand by deploying strategies like use of reflective material and integrating natural ventilation systems to decrease reliance on HVAC systems, reducing energy use for lighting by use of LED and automation systems and maximizing natural daylight, reducing energy used for heating water by deploying solar water heating systems, reducing equipments and appliances electricity consumption. All these measures collectively contribute to a more sustainable and cost-effective and energy-efficient building operations. To further create a better understanding with the help of case studies in detail, one and all must refer to the case and practices like Sustainable Energy Authority in Australia, passive design strategies in India and Ireland, for example, effective lighting in the Latvian Academy of Sport Education, and etc. This leads to the conclusion. The main themes that covered broadly throughout this module, energy management and audit, include: number one, objective. The energy management focuses on minimizing cost and environmental impacts while optimizing energy use to enhance profitability and competitive advantage. Energy audits are essential for identifying energy wastage and improving opportunities. They are categorized into preliminary, targeted, and detailed audits, each with a specific focus and depth of analysis. Next, we discussed energy conservation opportunities, or ENCON. This document emphasizes identifying and implementing energy saving measures categorized by cost and return potential to optimize energy usage. Technical and economic feasibility. Assessing the viability of energy efficiency measures involve evaluating technical feasibility, economic benefits, and impact on safety and production. Audit reporting. The audit report should clearly present findings, recommendation, and potential savings tailored for both technical and non-technical audiences. Implementation and monitoring. Post-audit, an action plan should be developed to implement recommended measures with continuous monitoring to ensure effectiveness and identify further improvements. In the upcoming lecture, we will delve into the new module, Building Codes and Standards, where we will be covering overview of building energy codes, compliance requirements for energy efficient buildings, and case studies in code compliance, and much more. Thank you for your attention, and I look forward to our discussion on these exciting topics. Thank you.